Okay, hello everybody. My name is Bruce. I am a mentor with Team 2852 in the FRC program, associated with Dennis Morris High School in St. Catharines, and we are called Dennis Morris High Voltage. Tonight we're going to take a look at rotational to linear motion. We're going to take a look at transforming rotational motion to perform a linear motion task. So converting rotational motion into linear motion, it's been around for centuries, many centuries. Why? Well, for one example, long ago, people needed water from the well. So they developed a hand crank attached to a drum, which moved the rope, which caused a linear motion of the bucket up out of the well. Rotary motion, linear motion. Modern technologies replaced hand cranks with electric or gas motors to provide the useful rotational motion that we need. Motors output rotational motion that is perfect for turning screws, gears, wheels, and drums. Robots, machinery, and even cars need to turn this rotary motion into linear motion. So can you think of rotary motion that is transformed into common linear motion in the world around you? Can you envision that in your head? Let's take a look at some examples. If you take a gas piston engine, attach it to a powertrain and some rubber wheels, you might get something that looks like this. If you have a gas piston engine connected to a propeller, you might get something that looks like that. And how about a gas turbine engine connected to a powertrain and caterpillar treads? You might get something like this. If you add some steering capability, you get a car, a plane, or a tank. So some common rotary to linear motion. What about our robotic needs for linear motion? We need locomotion. We need to make our robot move. Wheels or treads for moving the robot. You can also have legs and things of that nature. Lifting, elevating, pushing, or causing a gripper to open or close. These are all common robot tasks. Cable or drum lifts to raise or lower a carriage, or even the whole robot. In the following slides, look for the rotary motion and the resulting linear motion. So some simple actuators, drum and cable. Now this is a typical overhead crane. We have an electric motor driving through some gears, which will rotate a drum through an aircraft cable or a wire cable, through a pulley, which will give you a vertical motion. Rotary drum, vertical motion on the hook. Another common method, a threaded rod and a nut. Very simple. If the threaded rod is constrained to only rotate and the nut is prevented from rotating, as the threaded rod rotates, the nut will move forward. We could use something like that in a scissor lift, a screw jack. You can see there's a nut in this end. You can see the threaded rod spinning in and out and pulling those two pivot points together or apart. And this is the common method and the common jack that you will see in just about every car that's on the road today. So here's an old design, but still possibly used. It's called a Scotch yoke. And you can see a rotary disc being driven, has a pin on it which slides in a slotted yoke. and the slide actually causes a forward and back motion. Rotary motion to a linear motion. Now, a very common one is a crank and slider. Here we have a rotary wheel with a pin, a bearing, a connecting rod to a slider that's running in a slot. Rotary motion to a slider, giving you a linear motion. Where might this be used? A very common example is a reciprocating compressor. This is what they use to compress air in small applications. So you have a rotary wheel, and then there's a mechanism inside. The mechanism looks a little bit like this. The wheel turns the crank. The crank is connected to a connecting rod, and it's driving a piston up and down in a cylinder. You can see it drawing the purple cool air in, compressing it, and pressing the red air, the high pressure air, out. Once again, rotary motion causing a linear motion. Another old design that's been around for a long time is called a rack and pinion. Now here you see the blue pinion gear, which is being rotated, causing the green rack to move back and forth. Very common system, still used today, and the most common application, one of the common applications, is the steering in automotive cars. You can see once again the pinion, the small pinion gear, moving the rack, and the rack moves through a linkage, connecting rods, through a knuckle to make the wheels turn left or right. A cam and roller tappet, another common mechanism. You can see the lobed cam with the high point and then a bit of a circular section. As that high point rolls by that roller, it pushes that tappet up and down. And once again, this is another common application that's used in an automotive engine. And that cam is opening, in this case, it's the intake valve. You can see the intake valve, the spark plug, and the exhaust valve. And you can see that it's timed to open for a certain amount of time. And the cycle is intake, compression. Let's try that again. Let's see if we can get that better. So, intake, compression, power stroke, exhaust. And this is what's going on in the majority of the cars that have a 4-stroke engine. Here's another old design, something that's still in use though. It's a very simple step cam, which as it rotates, the roller will roll on that roller until the cam drops off the step and moves very quickly down. There, we've loaded it. Let's take a look at this. So you can see it preloads it, up we go, drop off, and very quickly drop down. So that would be a stepped roller design. Now, a Geneva index drive is not truly a rotary to linear motion, but it is a very interesting motion. It was developed in Switzerland as a watch drive long, long ago, and it looks like this. We have a green rotating wheel with a pin and a follower. The pin enters the Geneva index plate and causes one index for each rotation. And the nice thing about this design, you may be able to see it, you may not, is that as the pin enters and starts the motion starts slowly, accelerates, and then decelerates. So you get a soft start and a soft finish. So the index motion is very smooth. You don't get a jerky motion. And where we would use something like this would be for an indexing table in industry. You can see the motor underneath the table. It would be connected to a Geneva drive, turning that green wheel, and then indexing this table one step at a time. And then very common for machining operations, loading and unloading operations. So that's a Geneva index, clever device that's still in use today. We're going to take a moment and talk a little bit about linkages. Although once again, they're not true rotary to linear, but they are rotary motion that causes. Okay, we just dropped out.
Oh yeah, the presentation is.
It just dropped out on me. Okay, we're back. I think the cahoots bailed out and I lost the connection. So let's go back here. Okay, so bar linkages are a basic engineering design concept. They typically are described by the number of basic bar sections. For example, a 2-bar linkage, a 3-bar linkage, etc. The bars can have a fixed or moving pivot joint. Take a look at this 3-bar linkage. You can see 2 fixed pivot points and 2 moving pivot points. As we rotate one of these bars about the fixed pivot, we will get a corresponding arcing motion out of this pivot. So here's a common 2-bar linkage concept. And it may look a little bit familiar. If you replace the left bar with the wheel, you once again get a crank and slider motion. The fixed pivot point can be in the middle of the bar as well. And you can see this 3-bar linkage, how that motion might happen. Notice the parallel motion on this 4-bar linkage. Linkages are very useful, and there is just a ton of things you can do with them. And you can be very creative. Here are some real world common linkage examples. Recognize this? This is a typical scissor lift work platform. Can you see the linkages? We've got scissor linkages here, a series of them. Here's a 3-bar linkage. Can you see the 3 bars? We're sort of stretching a little bit, but the shovel is one of the bars. You can see its motion. Then we have the shovel arm, which is another bar section. And then we have the boom, a 3-bar linkage, which is a shovel. Now here's a clever linkage developed to provide a catapult motion. It's reminiscent of a steam locomotive drive that they call a choo-choo linkage. And I'm just going to have to wait while this loads for a moment. Okay, this is not loading for me, so we will have to move past this one. So let's talk about some modern actuators. Chain conveyors. Very commonly used in industry. We have, in this case, a poly chain, which is being driven around a sprocket. If you look over here, we have a motor through a right-angled gear drive, a shaft, sprockets that will pull the chain and give you a linear motion. Rotary pulley, giving a linear motion to move parts, boxes, whatever your product is. Timing belt, linear actuator. For those of you who aren't familiar, a timing belt is just a flat rubber belt that on the inside has essentially square teeth. These teeth mesh with sprockets that have a corresponding square tooth. And very popular because they are very accurate, give you accurate motion, there's no slippage, and they can also transfer high loads. And this is how they might be used for a rotary to linear application. You can see the poly belt here, a sprocket at top and bottom of this device, and then a table. The belt is connected underneath here at this point. And as we rotate the belt, this table will slide on these guide bars down and back up. Might look something like this. You see the motor turning the pulley, causing the plate, the base to move back and forth. So that would be a timing belt linear actuator. Now, perhaps a more modern actuator is a lead screw, which is really very similar to a nut and a threaded rod. So we have an electric motor going through some gears, turning a threaded rod. This pin would have a corresponding internal thread to it that would cause it to move back and forth when we rotate the threaded rod one way or the other. This is what it would look like in close-up. Here we have a threaded rod, which looks like it's got a square Acme thread. We see, in this case, a split nut, so it's nice you can see the inside of the thread. It has a mating inside thread for mating with the outside thread of the rod. In assembly, this might look something like this. A motor turning the threaded rod, causing the nut to move back and forth. You would attach something to this plate and you would get some useful motion. Now here is a modern actuator that is very commonly used in industry and industrial machines. It's called the ball screw linear actuator. A little bit like a lead screw, but a more complicated application, used specifically in high load in precision machining. So here we have a spherical thread. It's actually a spherical surface. And the ball nut, in this case, which is made out of plastic so you can see what's going on inside, has a mating spherical surface. And in between those two surfaces, they'd have very closely matched sized ball bearings. As the rod rotates, it causes the nut to move and the bearings will roll through the nut. And what they do is they collect the nuts they collect the ball bearings as they exit the nut, and they go through a recirculating tube, and you can see them coming back through here and going from one end and up to the other end. Expensive, complicated, but extremely accurate and as I say, will move extremely large loads. In application, it would look something along this line. You'd have a servo motor through a coupling, connect it to a ball screw, and then inside behind this plate would be a ball nut, connect it to the plate, and then attached to this plate, you could put a milling head, a drilling head, any type of operation that you need. You could use it as a press. And that is, as I say, a very common application in industry today. So that is the end of our presentation. So what I would like to do now is we have some quiz questions in Kahoots. And let's see if I can get us there. Now, Wayne, are you guys sharing my screen still? Are you seeing the Kahoots screen? Or do I have to share it?
Yeah. Yes, I can see it.
Okay. So anybody who is following along, if you would like to go to the Kahoots app, www.kahoots.it, type in that game pin number, and I see Nanook. Cami has joined. And is it pronounced Layla or Lila? Now, Wayne, I'll assume that you're not going to join because you've already gone through the questions, haven't you?
I've joined.
Oh, have you? Oh, okay.
I think you got to push start.
Okay, are we all set to go? Okay, so rotational to linear motion. I'll read the questions for you. A compressor is an example of a Scotch yoke. True or false? You are all correct. It is a crank and slider. Okay. Nanook is quick on the call here. How many degrees in a circle, everybody? 100, 180, 360, or 98.6? The correct answer is number 2. We're talking about a full circle. Okay, we've had a leader change. So a quiz. If a Geneva index plate has 6 slots, how many degrees of rotation for each index? And hint, use the answer for number 2. How many degrees in a circle? And the answer is correct. It's 60. If there are 6 slots and there are 360 degrees in a circle, 360 divided by 6 is 60. That's the math behind the Geneva index. Another lead change. True or false? Is the outer surface of a cam lobe round? And that is indeed false. The lobe, by its definition, has a lobe on it. So there is an eccentricity to the round surface or the surface that rides against the follower. Okay. We have a quiz. What device is commonly used in automotive steering? Is it a ball screw, a rack and pinion, cam and tappet, or a left-handed framtabulator? And if it was me, I would have said left-handed framtabulator just because I like to say it. Okay, we've got two correct answers again. True or false? When in use, a ball screw nut does not rotate. True or false? That is absolutely true. If the nut were to rotate, you would get no relative motion between the ball screw and the ball nut. And ladies and gentlemen, that is the end. Layla, number 3, Cami, number 2, and our winner is Nanook of the Northland. Thank you very much for playing. The last thing that I'm going to see if I can do is I would like to go back to the presentation and see if I can get this linkage application to load. Okay. Nope. Sorry, not the one.
Called a choo-choo linkage. And we've got a little Lego model here that we can show you how it works on. So we've got a small little gear drivetrain here, and I've got a crank on this side. So as you can see, we've got 2 bars that make up this linkage, and then we've got our gears down here. There's a stop on the other side of the gear, and that's really important for how this works. So as it cranks down, the stop pulls the first bar down so that it doubles over with the other bar. Now, once it gets over center like this, you can actually stop and take your hand off and let the motor power stop it there. And what this does, this system allows you to have your motor continually turning. And once the bar gets over center, it will completely release and launch your ball or whatever you've got on your catapult. And that's just what we're using. We're actually just using a single motor on that. So we get our full launch with only one motor compared to some flywheels. So it's a very effective design for this year's challenge, and it actually works very quickly for launching the particles.
So once again, that's the linkage that they use as a catapult motion. And as I say, they call it the choo-choo linkage. So that's just to complete the presentation. Thank you for your attendance and good luck on your Elegoo build.